Sorry, what the fuck?
That are fit for Python and Java, the agent copilot like code verification are simply not available in auto-active verifiers. The difference of how training data affects like copilot performance is seen in Lean, where with community adoption tools have become a lot better, and there's no reason for why this is not possible in Dafny and auto-active verifiers in here. And the human labor is really expensive. Writing Dafny tools as we've seen today can be 30 minutes per line of code in even mid-scale projects. And this is really bad if we want to scale this in the next year. So what's our solution? In the span of my internship, we identified a data set of the sort of problems that we could potentially look at and formalize into Dafny using the compiler feedback hints that we can track correctly. So such data set we looked at is verified. It contains around 13,000 programming concept problems in Python. Those Python solutions to the problems have reference test cases as well as some metadata that will. It covers competitive programming problems from LeetCode, code courses, and HackerRank, as well as other sort of online available building. The limitation of why this is not possible in principle is simply due to the fact that Python is in a very good programming language. It doesn't have the same type restrictions on specification synthesis. Is simply a very hard task. So a naive translation of Python to Dafny to get more data in Dafny is really good. Throughout this informed description of the problem, we came up with our translation pipeline, which leverages compiler feedback in Dafny in multiple stages and allows for the model synthesizing the program to self-correct multiple times. So first of all, when we get a problem into our data set, we synthesize its method signature. Our ground truth method signature that we will never change throughout the pipeline. From then onwards, we really want to make sure that the specification and the test cases are ground truth examples for that particular pipeline synthesis. And then we move into the implementation and proof stage, where we implement the implementation to the signature. And in Dafny, this happens all in one stage. So we add the necessary assertions as well to track. The reason why we chose this particular sequence is that once you're done with one part of the pipeline, then you can effectively freeze it and move on to the next step without going back sort of any further back than you need to. An example of how such a pipeline tracks is the following. If we have a very simple problem, such as implementing a function that checks if a given string is a palindrome, the question will be stated in natural language. We'll have a reference Python solution, which in this case is very hard to translate into Dafny because of the particular syntax used. And then we'll ask the model to generate only the method signature in Dafny, which is the output here. And then, given the method signature, we'll ask it to generate the specification on one side without generating the implementation at all for now. And then we'll ask it to generate the test cases in parallel. So both of these we can check given the method signature that they compile, with the compiler telling us that it's unimplemented yet, but at least we can check for syntactic correctness in Dafny. And these test cases are also translated naturally from the reference test cases that we see in Taco Verified. So once we have our sort of stage set of what the program will be aiming to solve, once we have the specification and tests, we can put them together. So in this particular case, the model came up with an extra predicate and an extra function for the palindrome method signature. Then it came up with the specification in the previous stage. We put the method for the test
below that in the bottom of the file. And then this is our ground truth. We fix that. We freeze the problem. We do not allow the model to change none of the test cases or none of the requires or ensures clauses. And we only allow the model to implement the method. And this allows us to, again, sort of safely implement as well as use Dafny error feedback to sort of bootstrap our knowledge as we go along. However, one of the limitations in all of this automated synthesis is that Python programs, they do not have specs given in the data set. You have to come up with the specification as you go along. And the two main problems we've noticed with specification quality are too restrictive of a specification, so specifications that essentially make the prerequisites too difficult. This happens less often than the second one, but we'll talk about the first one now. So if the specification is too restrictive, then if we take the specification, so all of the requires clauses for this particular problem and all of the ensures clauses at the bottom for this particular problem, and we require all of the test input assumptions, and we also require all of the output assumptions. So here we're fixing the output here, that is day, to be equal to 3. Then this should verify. We should be able to prove that in this particular instance, we should be able to derive the ensures clauses. In cases where we cannot derive it, it's either that the solver in and of itself is too weak, so Dafny simply cannot one-shot this lemma, and in some cases that's fine. But if in all of our test cases this is true, then it's a flag that our implementation, the specification we came up with, it's too restrictive. Another way that we can tackle this is on the other side, which happens a lot more. Sometimes specifications are simply underspecified. For problems that require optimality, such as finding the maximum contiguous subarray, the maximum sum in a contiguous subarray, you need to really state optimality conditions, and models that are not as good at Dafny really struggle with this right now. So the way to check for this particular instance we found is using two methods. First, we may attempt to prove a contradiction, assuming the output is not the ground truth value. So if you remember the previous example, here we will assume that in this particular instance, output day was equal to 1. We'll assume that day is not equal to 1, and we'll have all of the previous ensures clauses as now preconditions, requires clauses, and we'll aim to prove false. So this should be, in principle, provable. Again, depends on how good the Dafny SMT automation is for how many proofs that this actually comes up with. And in the other case, we may be able to not strictly prove false if the method, if the output is assumed to not be the ground truth example. But if we perturb it, then in the cases where we are still able to derive the post condition, it means that this particular output can range a variety of values, so it's underspecified. So these are the methods that we use to ensure specification quality, and we propagated this feedback from the compiler to the model as it was going through the pipeline to self-correct. So what did we get? Firstly, we instantiated the model with the pipeline with Claude Sonnet 3.7, and for the first stage of the pipeline, getting the specification and test cases, when you have the method, we have over 5,000 compiling files. Given these over 5,000 compiling files, so this is nearly a success rate of 50%, slightly less, then we went in and, freezing the specification and test cases, looked for implementations and proof of those programs. We found that through a fixed budget of error correction, we were able to synthesize 2,751 files solely from scratch, passing the specifications and the test cases and running the test cases without errors. Sort of something I'll come back into the future of this talk, we keep all of the positive and negative inferences for possible reuse later. So not only the 2,700 programs make it to the final data set, but we also keep all of the error correction chains that allowed us to find the final solution. I mentioned Taco Verified has metadata. And this is a snapshot of that metadata. It stores the problems into skill types. Although the success rates in most of them are sort of quite low on this on this graph, it really still varies by type. For example, there's problems such as sorting and range queries, which typically think about sort of mutable arrays and objects that don't think about a single element, but rather a group of elements, where the models are performing worse. And comparatively, on bit manipulation, for example, the models are performing comparatively better. So we need more data on this to think about where automatic code verification can be better or worse domain-wise, but there can be an early indication of such fact. Right. So I mentioned that I'll come back to the fact that we keep all positive and negative inferences for possible future reuse. We do this exactly in the way we create our fine-tuning data set. So given the data, all of the new Dafny programs we've generated, we needed to validate that this is actually useful for AI model training, because having more data is good, but we need to show that it's useful, that it's more useful than the stuff that the models are trained on beforehand. So to maximize efficiency, we not only look at the first top row of natural language decode synthesis data points, but we also split up all of the percentage is wrong. Sorry. We look at all of the possible other ways to synthesize these programs. In particular, we can look at implementation repair. This particular row corresponds to the fact that once we are implementing the fixed specification and test cases, if we make an error, then we might be able to use might be able to train on the fact that if you made a mistake, the error feedback was precisely this, and we fixed it in a particular way. So, for example, implementation infilling is this part of the pipeline where we ask the model to implement. It makes an error correction attempt and then comes up with a correct example. So to show our efficacy of our method, we evaluated on 2 benchmarks, which I'm sure will be discussed in the further talks in this session. We took a simple model that is known to be a good open source coding model, Qwen 2.5 Coder 7b, evaluated on 2 benchmarks, so DafnyBench and DafnySynthesis, one addressing simply proof infilling, so assertions, adding assertions to an existing implementation, and the other generating the Dafny implementations given test cases and a method. And we showed significant improvement from the base model, being quite competitive with prior frontier models during the benchmark release. So showing that this sort of synthetic data that we can generate really works. So to conclude, we have a data set of nearly 3,000 verified programs leveraging intermediate Dafny feedback. Soundness and completeness lemmas really help us get a higher quality of a specification during generation. we split our fine-tuning data set into multiple training examples per pipeline run. And this is a really promising way to train copilots for Dafny, is our conclusion.
I think we have time for one question.
So you were talking about translating the test cases as well, but actually the test cases, I imagine that they're like just comparison of function applications. So I guess you can actually have a faithful translation to Dafny.
Yes.
Like you don't need an.
So we found that in about half of the cases this is true. However, some types still don't match. For example, if you're thinking about a matrix, for example, the way you represent a matrix in Python versus in Dafny varies a lot. So you would still have to have that type translation, and we chose to automate it with LLMs in our model.
Okay, but because the type translation itself, I think you could like systematize that. And I don't.
It's possible, but we didn't want to equate for all of the cases sort of by hand.